I've said already quite a bit about the Laplacian eigenmap algorithm. So we have the graph, and what we want to minimize is this objective function here. And we want to successively do that. So, I mean, this is written for just one solution, y, but as I mentioned a couple of times, is that if you don't want just a one-dimensional embedding, if you want a 2 or 3 or 4-dimensional embedding, you solve this problem several times. Always sort of, first you pick the eigenvector with the smallest eigenvalue, or pick the solution that really minimizes this, and then you're looking for a solution that minimizes this subject to the constraint of being orthogonal to the already found solution. And that then leads to, as we have seen above, finding the eigenvectors and eigenvalues of the Laplacian matrix, and then you take just the first ones of these. So the first eigenvector is always the 1, 1, 1, 1 vector, which you ignore because it doesn't carry information about the structure. But then you take the second and third and fourth eigenvector, depending on the dimensionality at which you want to show or display or visualize the graph. So in terms of our algorithm, what you do is you first construct a similarity graph, then you construct the weight matrix and the degree matrix, and from that you construct the Laplacian matrix. Then you calculate the eigenvectors of usually the generalized eigenvalue problem. You could also use the ordinary eigenvalue problem, but usually it's a generalized eigenvalue problem, and you order the eigenvectors by increasing eigenvalue. So first the smallest one, which is 0, and then the higher ones. And then you can generate m-dimensional representation by taking the first m eigenvectors. And that's maybe I should emphasize this. So you would have so this is the first eigenvector, and this is the first component of the first eigenvector. And then you take the second component of the first eigenvector, and then maybe, let's say, the third component of the first eigenvector. Third. Okay, then you take the second eigenvector. Oops, sorry. Third, and let me take a fourth one. Okay, in this field, these are the eigenvectors. And these ones, so the columns are the eigenvectors, and the rows are the features that you would actually create. Yeah. So the index of the rows would be the nodes. So this would be first node, second node. Is that right? Yes. First node, second node, third node, while this is the first solution, second solution, third solution. So in this case, we have 3 nodes, and we generate a 4-dimensional embedding, which is a bit weird because usually you have many more nodes than you have dimensions, but the way I've written it here would be 3 nodes, which is a bit strange actually, because Because what? Because there are no 4 eigenvectors, right? So it's yeah. So we would actually imagine that this is going on, that you have more nodes in order to actually support 4 eigenvectors. So it's not possible to extract more feature elements than you have nodes. So in that sense, it's a confusing example that I've written here. But I hope you get the point. So the eigenvectors are in this direction, and the features that you extract are in this direction. Okay. So maybe actually correct this here. Okay, so now you can go and draw these 3 points in 3-dimensional space, and that would be embedding. Although for 3 nodes, usually a 2-dimensional embedding would do. Okay. Good. Yeah, so here we have 2 examples. So this example shows a data set, illustrates on the left side a data set with horizontal and vertical bars. So this would be the vertical and horizontal, and it's only one bar shown at a time, so they're both plotted here, but either you see a blue bar, either you see a vertical bar or a horizontal bar. The color is not given to the system, it's just a pixel distribution. So you have a lot of them, and you can imagine that there's a high overlap between the vertical bars if they're at similar positions of the horizontal bars, while the distance between any horizontal bar and any vertical bar is larger than the minimal distances within one group of bars. And if you now apply the Laplacian eigenmap algorithm on this with 2 dimensions, so you take the first 2 eigenvectors and you plot the combinations, so the coefficients of these first 2 eigenvectors as 2-dimensional vectors in this plane, you see this graph this structure, which reflects nicely that all the vertical bars form one group and all the horizontal bars form one group. And this is a plot in 2 dimensions. It would be interesting to see a plot in 3 dimensions, because then you would expect that this here actually looks like a 2-dimensional plane, because the bar varies in this 2-dimensional plane. So this was probably reflected if you would take the next eigenvector, right? So here, to be precise, we use the second and the third eigenvector, because the first one is the 1, 1, 1, 1 eigenvector. Yeah? If you do PCA instead, it's not very conclusive. So these 2 distributions would mix with each other. So here's the application for words. So you have a large corpus of text, and you characterize each word by its neighbors. So by the statistics over the neighbors that it occurs with. And then you define a similarity measure on that, so you can define for each pair of words define a similarity, depending on how frequently these 2 words occur in the same context, and then you do Laplacian eigenmap algorithm on that, and that gives you this structure. And what's interesting is if you zoom into this 1, 2, or 3 region, that's shown in the next figure, to show that in this one region you have all these kinds of verbs: be, find, make, say, look, etc. Here you have more. Okay, what is this called? Preposition. So these are infinitives, these are prepositions, and here these are modal and auxiliary verbs. So you see that the Laplacian eigenmap algorithm can reveal structure in the sense that nodes or samples that are similar to each other are grouped together in that space, and then you can plot them in this structure, and you can look at sort of the neighborhood relationship between them.